I want you to picture the last time you got into an argument with a search engine. You know what I mean, right?
Oh, I do.
You type in something really specific like, how to clean a Jaguar, and you're thinking of the car in your driveway.
A luxury car, yes.
And Google just excitedly spits back 5 million results about, washing big cats in the Amazon.
Which is, I should add, very dangerous for both you and the cat.
Extremely. But it really highlights this massive fundamental gap in technology. We think computers are so smart, but a lot of the time they're pattern matching parrots.
Exactly. They see the letters Jaguar, and they just match it to a database. They don't know what a Jaguar is.
That's the keywords versus concepts problem, isn't it?
It is. It's the difference between just processing strings of text and actually, understanding meaning.
And that is exactly where we're going today. We are going to unpack that invisible layer of the internet that tries to fix this very problem. We're talking about how we teach machines to understand context and logic and relationships.
We are talking about ontologies.
Right. And I can already hear people thinking ontology.
Don't tune out. I know ontology sounds like the kind of philosophy class you accidentally signed up for in college and then dropped immediately.
It sounds incredibly dusty.
It starts that way. I mean, if you go all the way back to Aristotle, ontology is the philosophical study of being.
The study of existence itself.
What does it mean for something to be?
Okay, that is way too heavy for us today. We are definitely not doing metaphysics.
No, we are not. In computer science, we basically stole the word and gave it a very specific, very practical job. We use a definition from a researcher named Thomas Gruber way back in 1993.
Okay.
He called an ontology a formal specification of a shared conceptualization.
You just made it worse. Formal specification of a shared conceptualization. That is absolute jargon soup. Break that down to human speak.
Okay, fair point. Let's break it down. Shared conceptualization just means we all agree on what the world looks like. If I say hotel, you and I, we both picture a building with rooms you pay to stay in.
We share that concept.
We share that concept. The formal specification part just means we write it down. We write it in a mathematical, super rigid language that a computer cannot possibly misunderstand. It's not a vibe. It's a rule.
So it's about taking the messy, sort of squishy way humans talk.
Right.
And forcing it into a structure that a machine can actually rely on.
Precisely. And to really see how this works, we have to climb a kind of ladder. We call it the ladder of formalization.
I like a good metaphor. Let's climb.
We start at the bottom with total chaos, and we end at the top with perfect order.
So what's at the very bottom, the first rung?
The bottom rung is just unstructured text. So imagine a messy Word doc, a random blog post, that email chain you've been ignoring.
Okay, so using our hotel example, this would just be the word hotel appearing in a sentence somewhere.
Yeah, exact. To the computer, it's just H-O-T-E-L. It has no idea if it's a building or a person's last name or a type of cheese.
It has zero context. Okay, so how do we step up from that?
We move up to terminology. Now you have a bucket of related words. Hotel, room, guest, price, booking.
But no definitions yet.
No definitions,
Yeah.
just a list of tags. It's better than nothing, but it's not smart. So we step up again to a glossary.
Aha!
Now we have the word hotel attached to a little text definition, an establishment providing short-term lodging.
That helps me, the human. But does the computer actually understand the word lodging, or is that just another string of letters to confuse it?
It's just more text. The computer still doesn't know how lodging relates to, say, sleeping. And that's why we need the next rung, the thesaurus.
Okay, like the book I used to use for essays in high school. Synonyms, antonyms.
Exactly. So this creates a little web of similar terms. Motel is a synonym for motor hotel. Expensive is the opposite of cheap. Now the search engine is starting to get it. It knows if you search for lodging, if I'd also want to look for accommodation.
We're getting smarter, but we still don't know how these things fit together structurally.
Right. And that's the next massive step up.
Yeah.
The taxonomy. This is a hierarchy, a family tree of concepts.
This is where we tell the machine that a motel is a hotel.
That's it. And a hotel is a building. That is a relationship, is the most fundamental relationship in all of knowledge representation.
Because it allows for inheritance, right?
It does. If I know that a building has a roof, and I know that a hotel is a building, then I automatically know a hotel has a roof without being told.
Yeah, taxonomy is just a tree. Real life is not a neat tree, it's a messy web.
And that is exactly why we have to reach the very top of the ladder,
Yeah,
the ontology.
the final form.
An ontology takes that tree, that taxonomy, and it adds everything else. It adds logical rules, attributes, all sorts of complex relationships. It doesn't just say a hotel is a building. It says a hotel has rooms, a room contains beds, and a guest pays for a room.
It actually models the business logic of the situation.
It models the reality of it. It adds axioms. These are strict, unbreakable rules. For example, a specific room cannot be occupied by two different guests at the same time, period.
So we've gone from the word hotel on a napkin
Basically, yeah.
to a fully functional, digital model of the entire hospitality industry.
That's the journey. And that model is the backbone of what we call the semantic web.
I want to get into the nuts and bolts of that, because when you say model, I'm picturing a diagram on a whiteboard. But for a computer, this has to be code. What are the actual building blocks?
So if you were to crack open an ontology, you'd find two distinct boxes. And I mean literally, in the theory, they are called boxes, the T box and the A box.
This sounds like Dr. Seuss. The T box and the A box, what's the difference?
Think of a board game, like chess. The T box, that's the terminological box, is the rule book.
Okay.
It defines what a pawn is, what a king is, and the rules for how they are allowed to move. It describes the concepts.
So car or person or hotel, those are concepts that live in the T box.
Right. Then you have the A box, the assertional box. That's the actual board state during a game. It describes the specific individual pieces. This white pawn is on square E4.
So my specific Honda Civic with this license plate, or this person, Brad Pitt, lives in the A box.
You got it. The T box is the abstract rules. The A box is the concrete data. And holding them all together are those relations we mentioned. You have is a relation for the taxonomy. But you also have something called meronymy.
Meronymy. Okay, that's a $5 word.
It just means the part-whole relationship. A car has a wheel. A hand has a finger.
Seems obvious.
It seems obvious to us,
Yeah.
but you have to explicitly teach this to a machine, or it won't know that if you remove the wheel, the car can't drive.
It sounds incredibly orderly. You define the rules, you add the data, and everything just works. But I feel like we're glossing over the fact that the real world is, well, it's full of contradictions. Logic is neat. Humans are messy.
Oh, absolutely. And that messiness is, it's where these systems often break. There's a classic logic problem in this field called the Nixon diamond.
The Nixon diamond, as in Richard Nixon.
The very same. It's the perfect illustration of the problem of multiple inheritance.
Okay, so this is when one thing belongs to two different categories,
Yeah.
and those categories don't really get along.
Exactly. Imagine you're building an ontology about people's beliefs.
Yeah.
You have two rules in your T-box. Rule 1, Quakers are pacifists. They oppose war.
Simple enough.
Rule 2, Republicans are hawks. They advocate for military intervention.
Now, these are generalizations, but for the sake of the logic puzzle, okay? Quaker equals peace. Republican equals war.
Right. Now, you introduce an instance into your A-box,
Yeah.
Richard Nixon. And here is the undeniable fact.
Yeah.
Nixon was a Quaker, and Nixon was a Republican.
Oh, I see the crash coming.
The computer looks at the rules and it asks, is Nixon a pacifist? The Quaker rule says yes. The Republican rule says no.
And the computer just freezes, explodes.
It just gets stuck. This
Yeah.
is why building these things is so hard. You can't just dump data in. You have to program axioms to resolve these conflicts. You have to tell the system something like, in the context of foreign policy, political affiliation overrides religious affiliation.
It's fascinating because humans, we handle that kind of cognitive dissonance pretty effortlessly. We just say, yeah, Nixon was complicated.
Yeah.
But a computer needs a yes or a no.
A computer needs a ground truth.
Yeah.
And that brings us to how we actually put all this on the web, the semantic web.
Right. I mean, if I look at the source code of a website, I see HTML that tells my browser, make this text bold or put this image here. It doesn't say this is a hotel.
Exactly. HTML is for display. The semantic web is all about meaning. And to build it, we use a tech stack that people often call the layer cake.
The layer cake. Okay, walk me through the cake. What's the foundation?
The bottom layer is the URI, the Uniform Resource Identifier. Just like a URL for a web page, every single concept needs a unique ID. You can't just say Jaguar. You need a specific code that means Jaguar the car, and a completely different code for Jaguar the cat. So there's zero confusion.
And the next layer up.
That's RDF, the Resource Description Framework. This is the grammar of the semantic web. It forces everything into a structure called triples.
Triples, right? We touched on this. Subject, property, object.
It's the atomic unit of knowledge. The sky, subject, is property blue, object.
It's almost like caveman speak. Me,
Mm.
hungry, food.
It is. But because it's so simple and so consistent, you can link billions of them together into this massive global graph of knowledge. And sitting on top of RDF is the language that lets us get complex.
OLL, the web ontology language,
Hmm.
which, by the way, should be WOL, but they went with OLL.
You couldn't resist the wisdom metaphor, I guess. LOL is where the real power is.
Yeah.
But it comes in different flavors.
Yeah, the notes mentioned LOL Lite, LOL DL, and LOL Full. That sounds like menu options. I'll take the LOL Lite.
Think of it like this. LOL Lite is like a checklist. It's for very simple constraints. This is a car. It has 4 wheels. It's easy for a computer to process, but you can't say very much.
Okay, so what's OWLDL?
OWLDL stands for Description Logic. This is like a flowchart or maybe a legal contract. It's strict, it's logical, and it guarantees that the computer can finish its reasoning without getting stuck. This is the industry standard.
And OWL Full.
OWL Full is like a philosophy textbook. You can say anything you want. You can get incredibly nuanced and expressive. The problem is it's so complex, there's no guarantee a computer can ever actually finish processing it.
It might just compute forever.
It might. So for most people building real-world apps, you stick to the flowchart, not the philosophy textbook.
So we have the tools, we have the language. Now, if I'm a developer and I want to build a smart medical app, do I really have to sit down and define what is a virus and what is a patient from scratch? Because that sounds like an absolute nightmare.
That is the ontology building crap. And the golden rule is, don't do it. Reuse what already exists.
So what's out there to reuse?
Well, there's a whole hierarchy. At the very top, you have what are called upper ontologies. These define the entire universe: space, time, matter, process.
Just the small stuff, then.
The basics. Then you have domain ontologies for specific fields. In medicine, there's a huge one called SNO-MED-DCT. In genetics, there's the gene ontology. But instead of just listing acronyms, I want to tell you the story of psych.
CYC.
Yes, this is really the grandfather of the entire field. Back in the 80s, a researcher named Doug Lennart realized that computers lack what we call common sense.
Right.
A computer doesn't know that if you hold a cup of water upside down, the water's going to fall out.
Huh.
It doesn't know that once you die, you stay dead.
Things we all learn when we're 2 years old.
Exactly. So Lennart started a project to manually teach computer all of reality. He and his team spent decades hand-coding millions of rules. Bread is not a liquid. Trees generally do not move.
That sounds like the most tedious job in human history.
It was Herculean. It was the ultimate manual struggle, and they built this massive, logically perfect model of the world. But it really showed the limit of that manual approach. It's just too slow to keep up with the real world.
So what's the alternative? We can't just type in every fact about every new movie or celebrity that comes out.
The alternative was the wiki revolution. Specifically, Wikidata.
Ah, now this I know. It's the database that powers Wikipedia, right?
It is, but it's so much more than that. While Psych was a few experts in a room, Wikidata is thousands of volunteers all around the world. It currently has, I think, over 60 million items.
Wow.
It's this massive, messy, wonderful knowledge graph. If you ask Siri, how tall is the Eiffel Tower? She isn't measuring it. She's probably just pulling a triple from Wikidata. Eiffel Tower has property height, first 330 meters.
So we went from a few guys in a room typing water is wet to a global community mapping the entire universe.
And now we're even moving into a third phase. We aren't even relying on volunteers anymore. We're using ontology learning. We're using AI to build the rules for other AI.
This is the inception part of the deep dive. How does a machine learn an ontology from scratch?
It reads. It uses natural language processing, or NLP, to scan massive amounts of text, textbooks, articles, websites, and it tries to reverse engineer the structure of that knowledge.
Okay, so give me the steps. How does it turn a textbook into a graph?
Step 1 is term extraction. It has to figure out which words are the important concepts, and it uses stats for that, like TF-IDF.
Whoa, hang on. TF-IDF. That sounds like a radio station call sign. You're listening to TF-IDF 109.5. What does the math actually do?
It stands for Term Frequency Inverse Document Frequency. It's a fancy name for a simple idea. It looks for words that appear a lot in the specific document, but appear rarely everywhere else on the internet.
Okay, make that concrete for me.
Sure. If you scan 1 million documents, the word "the" appears everywhere. High frequency, but it's not important. It's noise. But if you scan a medical paper, the word myocarditis appears a lot in that paper, but almost never in a cookbook or a sports blog.
So the math flags it and says, hey, myocarditis is special here. That's a key term.
That's a key term, exactly. So once it has the terms, it moves to taxonomy learning. It looks for phrase patterns,
Yeah.
like X is a type of Y.
I see.
If it sees the sentence, the influenza virus causes fever, and the Ebola virus is deadly, it starts to learn that influenza and Ebola are probably children of the concept virus.
And it builds the hierarchy, the tree, automatically.
It does. Then it tries to fill in the other relations using word co-occurrence. If the words doctor and hospital constantly appear in the same sentences together, it infers there's probably a works-at relationship between them.
And I feel like I have to play devil's advocate here. Machines are notoriously bad at context. If I say apple, does it mean the fruit or the iPhone?
That is the hardest part. That's disambiguation. And honestly, that's where a lot of the older methods failed. But this brings us to the so what. Why does any of this matter now? In 2026, we have ChatGPT, we have large language models. Do we even need these strict T-boxes and logic rules anymore?
That is the billion-dollar question, isn't it? Because we've all seen ChatGPT just make things up.
Hallucinations, they call them.
Right. It'll cite a court case that never happened. It'll say a chemical is safe when it's deadly.
And that is exactly why ontologies are making this massive comeback right now. Think of an LLM like a really smooth talker at a bar. He's charming, he speaks perfect English, but he might be lying straight to your face.
And the ontology is the fact-checker standing behind him with the clipboard.
Precisely. This is a new architecture called RAG Retrieval Augmented Generation. When you ask a modern AI a hard question, it shouldn't just guess the next word. It should first query a knowledge graph, an ontology full of data, get the verified facts, the triples, and then use the LLM to write a nice human-readable sentence about it.
So the ontology provides the ground truth, and the LLM provides the friendly, conversational interface.
Perfect summary. Without the ontology, the AI is untethered. With it, it's grounded in logic and facts.
Let's look at a concrete example of this reasoning power. The notes mention a syllogism.
Yes, this is what you get when you have that logical structure. Suppose your ontology has two simple facts. Fact 1, Mario is Italian.
Okay.
Fact 2, all Italians are born in Italy. Now, you never explicitly told the computer Mario was born in Italy, but because of the logic rules, the system can infer it. It can generate new knowledge from existing facts.
That sounds simple, but when you do that at a massive scale, that's incredibly powerful.
It's huge for search. If you ask Google, who is the Bishop of Rome? A simple keyword search looks for the exact string, Bishop of Rome. It might fail. But an ontology knows that Bishop of Rome is a synonym for Pope, and it knows the current Pope is Francis. It bridges that semantic gap.
It connects the dots so you don't have to.
It also stops you from, going to the wrong bank.
The river bank versus the money bank.
Word sense disambiguation. If you tell your self-driving car, take me to the bank, you don't want to end up in the river. The ontology looks at the context. Are we talking about deposits and cash or water and fishing? And it guides the decision.
It really feels like we're moving toward a world where the computer doesn't just display information. It actually digests it for us. It does some of the thinking.
That is the original semantic web vision, and we're not quite there yet. The challenge that remains is what I call the glue problem.
The glue problem.
We have millions of these little ontologies, a medical one, a legal one, a real estate one. But they don't always talk to each other perfectly. If the medical ontology defines a person as a biological organism, and the legal ontology defines a person as a corporation, you have a conflict.
And the system breaks down.
The dream is true interoperability. A web where all these knowledge graphs link up seamlessly, where your calendar talks to your car, which talks to the city traffic grid, which talks to your boss's scheduling software. They all understand the concept of being late in the exact same way.
A web that reads for us so we don't have to, that is both incredibly convenient and slightly terrifying.
As all good technology is.
True. So the next time you type a question into a search engine and you get that little knowledge panel on the side of the screen that tells you exactly who an actor is, when they were born, who they're married to, don't take it for granted. That isn't magic.
It's a T-box, an A-box, and a whole lot of triples working overtime behind the scenes.
Thanks for diving in with us. We'll see you on the next one.